Hello and welcome to lecture 3. So we're going to be talking about continuity. So it's 2.5. Okay, so given function f, we say f is continuous at a if the following is true. The limit as x goes to a, f of x equals f of a. Now, this seems quite a simple, short statement, but inside of this is three separate things. So firstly, this contains the statement that the limit as x goes to a, f of x exists. Okay. Secondly, it contains the fact that f of a is defined. And thirdly, that the limit is actually equal to the value of the function at a. And as we know, the limit doesn't require anything about the value of the function in its definition. Okay? So plenty of examples where the limit exists, and the function is not defined at that point, or the function takes a completely different value. Yeah? But inside this one statement, the language of maths, these following statements are consequences of that one statement. All right, let's do an example. So let's sketch the following picture. So let's axis like this. And let's do it this. Okay, look at this graph, and let's try and identify all the points where this thing fails to be continuous. All right, so actually what would be a good idea is if you pause the video at this point and just look at this and then try and for yourself to make a list of all the points you see here that fail to be continuous, and then which of these following reasons are the reasons why it fails to be continuous. Okay? If you do that, then what should you find? You should find that there are 3 points where it fails to be continuous. It's not continuous here, it's not continuous here, it's not continuous here. And it's not continuous at 1 because the value of the function is not even defined at 1. So this is an issue. So 2 fails right here. Yeah? And then here, it is defined, but the limit does not exist, right? The limit definitely does not exist here. So here, 1 fails. And here, the limit exists, right? The limit clearly exists, and it's equal to this value, whatever this is. But the limit is not equal to the value of the function, which takes a different value, right? So here, we have that 3 fails. So the solution is that f is discontinuous at the following 3 values: at 1, at 3, and at 5. Okay? Cool. Okay, let's consider a different example. Let's look at this function. Fine. There's 3 parts of this. So f of x is x squared minus x minus 2 over x minus 2. Okay. Second function is defined in a similar way, but it's not quite the same. and we set it to be equal to 1. So this is if x is not equal to 2, and this is if x equals 2. And the third function is this function, 1 over x squared if x is not equal to 0, and that's set to be 1 if x equal to 0. So our question is, where are these guys discontinuous? So functions A, B, C, discontinuous. Okay, well, let's check it out. So look at this guy. We do some algebra. We have x squared minus x minus 2. This is going to be x minus 2, x plus 1. That looks correct, right? So we're going to get an x squared, a minus 2x, a plus x, and a minus 2. Right? So if we do this factorization, and we look at this expression here, the top is just going to be x minus 2, x plus 1, and for x not equal to 2, then it just cancels and it's equals the function x plus 1. Yeah? However, for x equals minus 2, here, this function here, we don't say anything. For x equals, start again, for x equals 2, this thing is just not defined. It just becomes 0 over 0 because we have this factorization. Yeah? So for A, solution, A is not defined at 2, so it's discontinuous. Let me bracket around here. Okay, what about B? Here it is defined at 2, right? It is defined at 2, but we know that the limit as x goes to 2 of this function, x squared minus x minus 2 over x minus 2, this thing is the same as the limit as x goes to 2 of just x plus 1, right? Because this limit only cares, and the definition of limit means that we only care about x which is close to 2, but not actually equal to 2. So, so this function and this function have the same limit because they only differ at this point 2, right? And at this point 2, this guy is not defined. This point 2, this guy is defined, but we don't care because the limit doesn't care about the actual value of the function at 2, okay? But this limit is easy to find. It's equal to 3, but 3 is not equal to 1, right? So we have the limit exists, but it's not equal to the value of the function, so discontinuous at 2. I'm going to write that as a sentence. And this is not equal to the value of the function, which is f of 2, so at 2. Okay, third function, C. Here, as x approaches 0, then this guy is tending towards infinity. So this is something we've seen before. The limit as x goes to 0 of f of x equals infinity. Now, even though we can write this and it's a true statement, the limit does not exist as a number, right? So limit does not exist. And that's what we require in the definition of continuity. We need the limit to exist. And when we say it exists as a number. So limit does not exist at 0. So discontinuous there. And that's it. Okay, cool. Kind of straightforward, I hope. Huh? All right, so raise the board and do some more. Okay, let's talk about what continuity from the left or from the right. So we say f is continuous from the right if the limit as x goes to a plus f of x equals f of a, and from left if, so this is a definition, so it's if and only if and only if the limit as x goes to a from the left, f of x equals f of a. So it's the same game, except now we're talking about limits from the left and from the right, which we already learned about. And we need this because sometimes we're going to talk about continuity of a function over a closed interval, right? And if we do it over a closed interval AB, then we can only talk about continuity of A from the right and continuity of B from the left, right? If we want to talk about the function being continuous over everything inside this closed interval, then at the endpoints it's only going to be meaningful if the function is defined just on that closed interval if we talk about left and right continuity. So that's the point of these concepts, and we'll read that later. Okay, let's talk about some basic laws. Let's change color. Laws of adding and all the other thing, continuous function. So, if we have f and g, where f and g are continuous at a, then the following hold. Firstly, the limit, actually let's just write this in words. So f plus g is continuous at a to f times g is continuous at a, and 3 c times f is continuous at a. Okay, so there's another law, but before we go into it, let's talk about why we know this is true. Okay, so as part of f and g being continuous at a is that the limit exists at a, right? So if we look at this, we look at the limit as x goes to a of this function f of x plus g of x, okay? What's this? This is the limit as x goes to a of f of x plus the limit as x goes to a of g of x by the limit laws, right? Which we saw before. So by limit laws. Since both these limits exist, the sum, the limit of the sum is the sum of the limits. Okay? And by definition of continuity, this thing, the limit as x goes to a, f of x is just f of a. And this thing is just g of a. Okay? Which is the same as f plus g acting on the point a. So this new function f plus g has this property that when we plug x into it and let x tend towards a, then it turns out to be f plus g acting on a. Yeah? And the same for this guy, and the same for this guy. It's just following from the limit laws, right? Nothing surprising here. Here's another law. Oops. Function f over g is continuous at a if, so it's not necessarily always true, but it's true under what condition? Well, if we think about what makes this work, it works because of the limit laws. We'd like to apply the limit laws for the quotient, but we know it's only true if the limit of the bottom is non-zero. Now the bottom is the limit of g, and g is continuous, so the limit as x approaches a of g is actually g of a, right? So we need that thing to be non-zero. So this will be continuous at a if g of a is not equal to 0. Cool. So we can do stuff to functions like this and still have continuous functions. And that should give you some idea that actually there's lots of continuous functions. So from the limit laws before, we found that polynomials were these functions which satisfy this direct substitution property, which is actually the same as being continuous. We found that rational functions were, so long as they're defined in the domain. And the same reasoning says that a whole wide class of functions are actually going to be continuous on their domain. So let's write a long list of classes of functions for which this is true. So the following functions are continuous on their domain. Okay. Polynomials, rational functions, trig functions, log functions, exponential functions, inverse trigs, okay, but note that I specify on their domain. Doesn't necessarily mean that they're continuous everywhere. They're not necessarily defined everywhere. So maybe here, maybe more precise about that. So we say f is continuous on AB if and only if it's continuous at every point in AB. And if it's a closed interval, as I mentioned before, then we can only talk about continuity at the endpoints in terms of one-sided continuity, either from the right or left. So if we are a closed interval like this, then we have to take right-sided continuity because we can only approach A from the right. Okay. So if we have a closed interval like this, then we also have to have one-sided continuity, but this time from the left. But let's not change that here, otherwise the whole statement is no longer true. Okay, so that's what continuity means on intervals. And what about these guys? Which ones do we have that are continuous on the entire real line? Well, polynomials for sure, right? Polynomials perfectly fine on the entire real line. The limit exists. They satisfy the direct substitution property. We have no problems with that. Rational functions, no, right? Rational functions only on the domain. So, example, f of x equals 1 over x. That's a nice rational function, right? It's a polynomial of a polynomial. Looks like this. Yeah. Its domain is everything except 0. It's not defined at 0. And everywhere except 0, it is continuous. And at 0, it's not, because even the limit doesn't even exist at 0. Right? So this guy is continuous on its domain, but not the entire real line. Trigonomic functions. Sine and cosine, they'll be fine, right? They'll be defined everywhere, continuous everywhere. Tangent, as we saw, not, because it has these vertical asymptotes at this minus pi, plus pi, minus pi over 2, pi over 2, and then all pi periodic, and then it's continued pi periodically, so it has, let me draw it, it has this shape right here, minus pi over 2, and then it's repeated pi periodically, so it repeats like this, so we have 3 pi over 2, and so on. So at all these points here, which are just pi over 2 or minus pi over 2 plus pi or 2 pi or 3 pi, we have an issue. It's definitely not continuous there. Okay, log functions are only defined positive numbers, right? So this is what log looks like. So again, that's their domain and they're continuous there. Exponential functions are defined everywhere, right? And they're continuous there. So this is another guy which is continuous on the entire row line. Inverse trigs depends on what you're talking about. Some inverse trigs, so the inverse of tangent, as we're going to see, is defined on the entire real line and is continuous there. Some inverses are not defined on the entire real line. Okay. All of these are elementary functions which you should be able to visualize in your head at this point. And some of you probably can, but many of you can't. And if you can't, that is a gap you have to close as quickly as possible. So the way to do this is you write down an example, write down a trig function, write down log or an exponential or an inverse trig, and try and figure out its graph. And we're going to do this in a second for inverse tan. Try and figure out its graph. And once you've done that, once you've done it once, it's probably going to be enough and you'll have it in your head. And if not, then the next time you see it, if you can't visualize it, then again, figure it out. At most, you do this two times. Figure out the graph 2 times, and you'll have it. You'll have it in your head, because we're going to be dealing with examples built up of polynomials, rationals, trigs, logs, exponentials, and if you can't visualize, if you don't see what these things are, it's going to make this much harder. So the sooner you get comfortable with these things, and there are not that many of them, the easier this stuff is going to be. This is the most efficient way to do it. Nail down this foundation as quickly and as solidly as possible. Don't be hazy about what any of these guys actually look like, and then just have all the stuff which is defined in terms of them be some kind of hazy mess as well. It won't take you 2 hours to be completely solid about the graph of every single one of these classes of functions, right? Spend that time rather than spend thousands of hours being unclear on all these examples that use these things as we go forward in the course. All right, so those are functions that are continuous on their domain. Let's do this example. Example 6. Where is this function, f of x, which is equal to log of x plus tan to the minus 1 of x over x squared plus or minus 1. Continuous. Okay, so because of these laws we've just learnt about, if we add functions, divide them, multiply them, they're still going to be continuous at these points, so long as they're continuous individually. We just have to think about the individual continuity properties of all of these things, right? So log is only defined for positive numbers. This guy is log, of course, but it's continuous on its domain. That's fine. This guy will be continuous on its domain, but we have to think about what its domain is. Maybe you're not comfortable with tan to the minus 1 yet. I'm going to figure it out in a second. This guy, well, this guy's continuous everywhere, but we can only guarantee that the quotient of these two functions are continuous so long as the bottom one is non-zero, and this thing is only non-zero if x is either with x squared is not equal to 1, so long as x is not 1 or minus 1. Okay, so we definitely have an issue here where x is 1 or minus 1, right? But outside of this, so long as we have a positive x, it looks like we might be okay, so long as tan to the minus 1 doesn't give us problems. So let's think about what tan to the minus 1 actually looks like. So maybe I can squeeze it into this board somehow. So we know what tan looks like. We did it here. Okay, here's tan. Here is tan. And what happens? As x gets closer and closer to pi over 2, then we go to infinity. And as we get closer and closer to minus pi over 2, we go into negative. But then we see the same thing happening repeated over and over again. So you have to think about this. So if you take a line like this, okay, you might have heard the horizontal line test at high school. What does it mean? It means that if we take some value here, we're thinking about all the x that map onto this value. And for tan, there are many, right? So there's this, there's a whole infinite range of them, right? And when we invert a function, we want to unwrap it, right? So what does inverse do? We want to be able to unwrap tan. So we take some number, we act on it with tan, and then tan to the minus 1 puts it back to x, right? But if tan is equal to L, then trying to find the x that maps onto L, well, there's lots of them, right? So we can't map it back to any individual x. So it's not meaningful to try and invert this, yeah? Unless there's only one value that hits L, right? So the horizontal line test you might have heard is that if there is only one thing that hits any horizontal line, then you can invert the function, right? And here there are many. So what do we have to do? We have to restrict the values of the inverse of tan to some range, and we choose the simplest, most obvious range, which is from minus pi over 2 to pi over 2. Because in this range, there is only one x that's going to hit every value of L, right? And in this range, from minus pi over 2 to pi over 2, then tan is going to go all the way from minus infinity to infinity, right? So tan sends minus pi over 2, just do an open interval, pi over 2, all the way to minus infinity to infinity, okay? And the inverse is going to do the reverse. It's going to send minus infinity to infinity all the way to, or squeeze it down to minus pi over 2 to pi over 2, right? So tan to the minus 1, sometimes called arctan, is going to send minus infinity to infinity all the way to, or squeeze down to this range. Yeah? Okay, so let's think about what it will actually do. Again, let me try and just squeeze it in somewhere here. So, what will tan do? Tan, actually let's change this color. Tan will send numbers which are close to pi over 2. So, just for simplicity, I'm just going to write pi over 2, and it's going to send it to infinity. Now, this is not to be taken literally because infinity is not a number, but I just don't have space to write numbers close to pi over 2 towards infinity. So I just write this. It sends things close to pi over 2 to things close to infinity, right? And it'll also send things close to minus pi over 2 to minus infinity. So 10 to the minus 1 has to unwrap it, right? It has to do the exact inverse. So infinity to pi over 2 and minus infinity to minus pi over 2, right? And both of them, tan sends 0 to 0, so tan to the minus 1 sends 0 to 0. So let's try and draw it, right? So tan to the minus 1 is sending the entire real line just to this interval, from minus pi over 2 to pi over 2, right? But it's defined for the entire real line. And out here towards positive infinity, we have a value which is close to pi over 2. And towards negative infinity, we have a value which is close to minus pi over 2. It's kind of looking like this, right? It's kind of looking like this. That's what it's looking like. So this is tan to the minus 1 of x, i.e. arctan. Arctan is actually quite a useful notation because sometimes students think tan to the minus 1 means 1 over 10, which is not what it means. Okay? It's arctan, it's got a, this confusion is taken away. Okay, but what do we see from this? Well, it's a perfectly well-defined, nice function, right? We have no problems with this guy anywhere. So, only possible issues we can have with this thing is we need x to be positive, we need x to be x squared minus 1 to be non-zero, in other words, x not to be equal to 1. And outside of this, then this thing is continuous. So f is continuous on 0 to 1 and 1 to infinity. And that's it. Okay? And we broke this down using these facts that we know, but most of all, just thinking about the pictures, thinking about what these elementary functions look like, right? Yeah. And this is an example. If you weren't clear what log looked like, you'd have a problem, and same with tan to the minus 1. And that's what I've seen. I've seen exactly these kind of questions on exams. And even if you study carefully limit laws and you know the basic stuff, if you have no idea what tan to the minus 1 looks like, then you're stuck. You can't do this question, right? So take my advice, get solid on these elementary functions straight away, and that's the most efficient way to do it. Okay, let's erase the board and do some more examples. Okay, so we're going to talk about a theorem which when I first write it down, it's going to seem kind of like somewhat complicated, but then we're going to draw pictures, and its meaning and its truth will be very, very clear. So don't be put off by what it first appears like. So a theorem. Suppose we have two functions. And the limit as x approaches a of g of x is equal to b. And f is continuous at b. Then, let's put it here, the limit as x approaches a of f of g. Let me change the pen. Okay, I have a change of color. F of g of x is equal to f of b. Sorry about this multicolored statement of the theorem. There's not that many little squiggles in M. And the limit. Okay, so pictures. clarify this. Let's draw a picture of G, and let's draw a picture of F. So this is G, and what information do we have? The limit as we approach A is B. So let this be A, and something like this, and this is B, right? So what is the information from this? It means that as we restrict the values of x to be closer and closer to A, we can force g of x to be an arbitrarily thin strip around B, right? That's exactly what this means, right? So we can take any thickness of the strip around B, we can take a tiny, tiny interval around A, not including A, and force g of x to be that close to B, right? That's what this says. So let's put a star here. So star is represented by this picture. Let's draw another picture. This will be F. Okay. Start here. What's information about F? F is continuous at B. So this is B. And this thing is f of b, because the limit as x approaches b of f of x is f of b. That's the definition of continuity, right? So for any thin strip around f of b, we can guarantee we get that close to it, so long as we are close enough to b itself, right? So for any thickness of strip around f of b, we can get that close by restricting the values of x to be sufficiently close to b but not equal to b. Okay. Actually, in this case, equal to b because it's continuous. So also equal to b. All right, cool. So that is this information. So this thing here, this is star star, that is given by this. So I'll just put an arrow, right? Cool. All right, and what's the conclusion? That the limit as x approaches a of this composed function is f of b. Well, let's take a look. So as we get x closer and closer to a, right? So this would be our x here. Then by the first information, we know that g of x has to be very, very close to b. It has to be in this thin strip around b. So g of x lives inside here, right? But we take g of x and then we apply f to it. So we're down here on the real axis now because we're about to apply f on it. But we know it's incredibly close to b from this picture. So g of x lives inside here, right? But if it lives inside here, by the fact that f is continuous at b, then f of g of x is actually in this thin strip around f of b, right? And as we take x closer and closer to a, then we are forcing g of x to be closer and closer to b, which means we are forcing it to be closer and closer to b right here. And as we do so, we can force f of g of x to be closer and closer to f of b, right? You think about that carefully for a little bit, you'll come to the conclusion that is exactly the statement, that the limit as x approaches a of f of g of x is f of b, okay? These pictures contain the information of the hypothesis and contain the reason why this is true. You know, the meaning of this is this. And this is what you have to do when you learn some new theorem, some new truth in maths. You have to unwrap it in terms of these pictures. You have to have pictures that make this make sense. Because this is the meaning. So if you're not used to doing this, or if you just watch this for the first time, you might not get it. But play this part again. Convince yourself that I am not cheating you. I'm not doing anything weird. It's completely, yeah, everything I'm saying is completely true, and you can check for yourself. This is indeed this picture. This is indeed this picture. And this truth is what happens when we just check out what happens as we let x get closer and closer to a. We follow the information of the pictures. And yeah, that's what you should do for all of this stuff. And in this course, I'm going to draw you these pictures all the time. But this is what you need to do to understand maths in every course you do going forward. And in later, higher level courses, there might not be time, your professor might not break it down into pictures to this extent, but to understand it for yourself, this is what you have to do, and this is what you can do, because this is actually what is going on. This is a language to describe these pictures. This stuff is just a more efficient way to describe these pictures right here. Right? And we could teach math or calculus without any of these symbols, just write things in words, but it would be incredibly long and slow, but it would still be about describing these pictures and these things. Right? So this stuff is just an efficient language for these pictures. But the pictures are the real thing. The pictures are the real thing. Okay, so this has a nice consequence. So consequently, if G is continuous, so if it's continuous at A, then that's stronger than the limit exists and equals to B. It actually means that B is just equal to G of A. Okay, so this statement is stronger than this statement. We actually know what B is. It's equal to G of A. Then, just by applying this thing, so since it's stronger, we can apply the theorem, but now B is G of A. We have that the limit as x goes to A of f of G of x is equal to f of G of A. Right? It's exactly the same statement, just applying the statement for this stronger condition when we know what B is. i.e., if f is continuous at G of A and G is continuous at A, then the composed function f composed with G is continuous at A itself. Because being continuous at A itself is exactly this statement, right? This statement is the same as this statement, right? And under these hypotheses, we can apply this theorem, and we have this conclusion. Cool. All right, so this allows us to deal with some other examples. This is example 9. Where are the following continuous? And our two functions are h of x, which is sine of x squared, and the other one is capital F of x, which is log of 1 plus cosine of x. Okay, solution. Okay, h shouldn't be too hard, because from what we learned, we are okay so long as, so this is a composed function of x squared and sine, right? So as long as the inner function is continuous at A and the outer function is continuous at G of A, where G is the inner function, then we're fine, right? X squared is always continuous everywhere. Sine is also always continuous. So there's no way this can go wrong anyway, right? So h is absolutely fine. So h is continuous everywhere. No problems with that. What about f? Well, f is a bit more of an issue, right? So log is only defined for positive numbers, right? And this guy is not always positive, right? So when cosine of x is -1, then we have a problem. So let's sketch the graph of cosine. Here at pi we have a problem. We're back like this, and then it repeats itself, right? So here at 3 pi we have another problem. Okay. So if we think about what happens, as x gets closer and closer to pi, right? 1 plus cosine of x gets closer and closer to 0, and the graph of log, as we know, is like this. As we get closer and closer to 0, log goes towards negative infinity, right? So we see, actually let me not write this. We see that f is not continuous at pi, 3 pi, 5 pi, minus pi, and so on. In fact, we can write all of these odd multiples of pi as 2k plus 1 times pi for k is an integer. Right? Just from thinking about what happens, right? Once again, just look at this. As we let x get closer and closer to pi, 3 pi, any of these values, then this thing in the center is getting closer and closer to 0, and then we're acting on it with log, and we're being sent down towards negative infinity, right? So that thing cannot possibly have a limit there, which is a number, and therefore we have that this thing cannot possibly be continuous at any of these multiples of pi. Right? Cool. So that answers that. All right. Now we're going to talk about another theorem, intermediate value theorem. Intermediate value theorem. So, often abbreviated to IVT. Okay, what does this say? So, suppose f is continuous on the closed interval AB, and n is between f of A and f of B, then there exists some C such that f of C is equal to n. Okay, so as promised, it's a theorem. It comes with a picture that explains it, which I'm about to draw. But a very good exercise for you watching on video right now is to pause the video, draw a picture that includes these hypotheses, okay, and try and see why that picture gives you why there is some C such that f of C equals n for any n between f of A and f of B, right? Draw a function f that satisfies these hypotheses, and then try and express the hypothesis and see why the conclusion is true. Okay, and once you've done that, then press play again and see how close the picture you come up with is to what I'm about to show you. Okay, so what's the picture? So we have a function which is continuous on the closed interval, right? So let's draw nice graph. So here is A, here is B. And what does it mean to be continuous on the closed interval? It means the graph looks something like this. And recall, being continuous on the closed interval means we're continuous from the left at A and from the right at B. Right? So this is our graph of our function f. Okay? And if we take some value of the function f of A f of b, okay? We take some value n between these two things. It's not a very straight line. We can see there is indeed a point C here where f of c takes that value. We can see that's true, right? And indeed, it's got to be true for every single n we take between f of a and f of b. Right? In fact, if we take n like this, then there's actually multiple points C that take this value. Yeah? Cool. And note that the hypotheses are necessary. If the function was discontinuous, then we could have a break in the graph, and then it clearly wouldn't be true. We could just pass the horizontal line through the break. If it wasn't continuous from the left or the right, again, it wouldn't necessarily be true. We could pass the line through this break at the edge. Yeah? The only way it's true is with all the hypotheses that we have. But from this picture, it clearly is true. Right? It clearly is true. Yeah? There's always at least one C for which this is true. And in fact, in many cases, there are going to be several of these C's. And this allows us to actually answer some questions. Did I lose my notes? So, here's a nice example. This is example 9. Show that there is one solution I should probably say there is at least one solution to this 4x to the 3 minus 6x squared plus 3x minus 2 equals 0 in between 1 and 2. Okay, so let's figure this out. So this is some cubic equation. There is actually some explicit formula to solve it. We're not going to use that. It's not asking us to find what the solution is. It just shows there is at least one solution between 1 and 2. So I don't know particularly well what the graph of this function looks like, but it's a polynomial. It's a continuous function on the closed interval from 1 to 2. Right? This is 1. That's not a very good 1 to 2. Let's do that again. It's definitely not at scale. So this is 1 to 2. And what does it mean for there to be a solution? It means that this function, so if we let f of x be 4x to the 3 minus 6x squared plus 3x minus 2, it means that there exists some x, so f of x is equal to 0, right? So it starts to be in the format of the previous theorem, the intermediate value theorem, right? So if it's the case that the graph of this function is something like, let's choose a different color, like this, where it goes from underneath 0 to above 0 or the other way around, then the graph has to be cut through by this line at y equals 0, right? Which is exactly the same as saying there exists some x such that f of x equals 0. Yeah? Cool. So, you guys don't know the explicit rule, well, almost certainly don't know how to explicitly solve cubics. If you saw this question on an exam, this is what should come to mind to you. This would be a harder exam question, but not an impossible one, right? It might come in with a hint in the intermediate value theorem. This would be an extended response question. Yeah? This question of asking for a solution of this is the same as this, and that puts you in the territory of intermediate value theorem. Right? So what we need to do is to check that f of 1 and f of 2 actually on either side of 0. And if they are, we're all set. So let's check it out. So f of 1, what's it going to be? It's going to be 4 minus 6 plus 3 minus 2. So it's minus 2 plus 3 is 1 minus 1, so it's minus 1. Right? So f of 1 is down here. F of 2, it's going to be 4 times 8 minus 6 times 4 plus 6 minus 2. So 4 times 8, 16, 32. Oops, 32. Minus 24 plus 4. So that's going to be just 8 here, and then plus 4, so it's 12. So indeed, we are crossing the horizontal line like 0, because we're all the way up here at 12. And this is like here at minus 1. Yeah. So by the intermediate value theorem, there exists x such that f of x equals 0, and we've answered this question. We've shown that there exists at least one solution to this equation between 1 and 2. Yeah? Cool. All right, so that's it for today. I will see the Wednesday group on Wednesday. Have a great day.